So next up, we are very happy that the co-founder and CEO of Earth Science Analytics has found his way to us, bringing more than 20 years of experience in the E&P industry with him, as well as an exciting presentation on integrated AI-assisted data analysis in a cloud-native environment, towards data-driven decisions in petroleum exploration and production. Eirik Larsen.
Thank you. Oops. There we go. It'll be a good idea to start at the beginning of the slide deck. So, thanks for the introduction. Thanks for inviting me. As was said, I'm Eirik Larsen, and I'm from Earth Science Analytics. That's a startup company based in Norway. And I'm a geologist working in the petroleum industry. So my entry into the machine learning world came as a result of feeling that we needed some tools to do things differently, more efficiently, and in ways where we can exploit all the data that we have available. So I'll focus on some points related to all that and how we may use machine learning for petroleum exploration in a way that geoscientists can drive this technology, and where we can exploit web-based software and cloud compute to make this useful tools in the daily life of geoscientists. So as geoscientists, both in the petroleum sector, in mining, and I'm sure also when you work in geological surveys, you are supporting people who are making decisions. So that's part of our job, to make the basis for these decisions. And just as an example from my world in Norway, the graph here is statistics on the discoveries we have made, basically covering the time span of my active career. And it compares the pre-drill estimates with an estimated mean in black, and the uncertainty as this green bar. And what we see is that after we have drilled and discovered a new accumulation of hydrocarbons, it is usually overestimated. And not even that alone, but the uncertainty bar that we have on our predictions is there's something wrong with that, and the real results comes in outside of the predicted uncertainty, and usually underneath. So we're consistently overestimating these volumes. So I think it's in the nature of us who deal with exploration. We kind of have to be optimists, but the data shows clearly that we are consistently over-optimistic. So looking at statistics like that, it comes to mind that this problem cannot come from the data alone. It must come from our psychology, our cultures, our wish that my prospect shall be reach the top of the competition and be chosen by the management to be drilled and things like that. So the idea is that we have all this data. If we manage to use it properly, data-driven, consistently, there would be a chance that we can make these decisions better and less biased. And as I said, I'm from Norway, and we're lucky in Norway. We have a fantastic national data repository for petroleum data. There are some numbers here of what's inside it, but there's enormous amounts of data. So not any human has looked at even a fraction of all this. So now we're trying to exploit this emerging technologies, machine learning, cloud computing, etc., to exploit that. So the first section here will be on the cloud-based platforms as a vehicle to make all this stuff available. So the state itself provides the data on their platform, which is a very good start. But they didn't think about the fact that the future will require this data to be machine readable. So a lot of PDFs and other data formats are in these archives. So we have done something about that in my company to build cloud-native and web-based platforms to make all that data available. So in the browser and in the cloud. So you can access all of that anywhere, anytime, from any device that runs a browser. So at the first look, it looks pretty much like a GIS system, but there is a difference from most GIS systems in the fact that underneath the surface of the Earth, we have access to the data that we have from boreholes, well logs, core data, fluid samples, and also seismic surveys. And also in the browser, we have built all the software that is needed to interpret all of this data. So seismic interpretation software, I'm sure many of you are familiar with. So you can interpret the data manually. And there's similar or more classical technology to interpret all the data types manually. And now comes the new, more aligned with the topic of the conference. How do we use AI, or when we say AI these days, typically we mean machine learning and deep learning, but how do we use that to automatically interpret this data? So now we have it available. How can we use AI to interpret it? But just to introduce the seismic data as a transition, I just wanted to show this. It's the colorful line is a seismic line. It's a vertical section through the Earth with reflections. It's kind of like ultrasound, but it's really low frequency sound wave reflections from layers in the Earth. And one of the things that we do as petroleum geoscientists is to map the faults, the discontinuities in the Earth that happen when earthquakes happen. So these black and white or grayscale images below, they are the classical manifestations of how we have done this in the past. So we can hard code some algorithms, kind of like image processing algorithms that highlight these discontinuities. But they're all functions of the image on the top. But it's hard-coded, so somebody clever figured out this algorithm that will create this picture. So we see the faults, these kind of semi-vertical black lines here, but it's not perfect. And any one of these does not give the complete picture. So we tried in the past to kind of combine them to get to better solutions. But now, with deep learning, this has kind of radically changed. And so Earth Science Analytics is by no means the only company who's doing this. I think we saw an example also yesterday. And this is the automatic fault interpretation with deep learning is a real example where this disruption is happening. So you can input the seismic 3D seismic data sets and basically output the fault interpretation with probability, with uncertainty in a detail that humans are not able to compete with anymore. So both in terms of quality and of course in terms of efficiency. So you can imagine hand interpreting all the faults that we see here. It would take forever, but with these machine learning algorithms, this is down to 2 hours if you can afford a multi-GPU. So just go back to this one and make a point that the deep learning network that did this job actually never was exposed to any real seismic data. And it was never exposed to any human interpretation. nor any of those seismic attributes that we used to do when we interpreted faults. So it was purely trained on synthetic data, so synthetic Earth models and synthetic seismic that goes along with it. But it turns out that the problem of identifying faults is simple enough so that we can come as far as this, and I'm sure also further, simply by training the deep neural networks or using a simulator. And these examples are slightly different. So you see the two most colorful images here are kind of cut in two. So on the right side we have labels. These are expert annotations. So geoscience experts have interpreted the data on a part of the data set. This is used as the labels into the deep learning algorithms. And the seismic data itself is used as the feature set. So for complex problems that is hard to make a simulator for, we can kind of embed the expert knowledge into this labeling or data annotation process and have the deep learning algorithms complete the work. So you get away with interpreting definitely less than 1% of the data, and the machine does the rest for you. So it's enormous speed up, and I think also some of these images suggest that the machine is actually doing a better job than the human labeler, which is kind of a problem that we're dealing with, because this cannot be measured with the metrics. We use metrics to quantify the performance of our models, but we measure how well does it perform versus the so-called ground truth, which is our human annotations, but they are not perfect. So when we see the output, it kind of looks better than the label set. I think one of those images suggests that. So how to deal with that problem in terms of metrics, because we need to use metrics to make these decisions and not make them subjective. So some other examples, more stratigraphic units, more faults, and on the bottom we have in yellow some complex channel systems from New Zealand, interpreted with deep learning, and in pink some so-called sandstone injectites. These are sandstones that are pushing their way up through the overlying shales. And these geometries are so complex that, of course, you can manually interpret them, but it takes ages. And these automated interpretation tools of the past, like auto trackers, they don't perform on this type of task, because it's not about following a consistent seismic event. It's kind of all over the place. But they're very much suited for deep learning predictions. That's just an image of how these sand injectites look like in 3D. So with that type of task, we're trying to push the boundaries by moving from annotating these on one seismic survey and then predicting them on the entire survey based on the sparse annotation, to a state where we can have models that are trained on multiple partially annotated surveys, and that the models can generalize to more or less any survey. So that would be much more convenient for the general user just to open the software, say, this is my survey, give me the sand injectites interpretation, instead of having to build a model from scratch. And this is an example of those channel systems from New Zealand, also here in yellow, in the image to the lower left. And it turns out that we can do this interpretation probabilistic, which would be even harder to achieve manually, because we would have to do a very time-consuming task many times. And here we have done it 250 times, but using neural network. So it's a technique, it was published by, I think, Gall and Kendall in Cambridge a few years ago. So those of you who do machine learning are familiar with dropout as a regularization technique, but simply use dropout also during prediction, randomized. so that each prediction is slightly different than the other. And so you basically make 250 predictions in this case, and we can stack them in various ways to have measures of uncertainty or probability of this particular geobody. So from that you can extract the average geobody shape, or you can calculate the volume within the geobody for each of the realizations, which is what we did in the histogram here. So we've just binned it. So now we have a probabilistic volumetric estimate for this body as a function of interpretation and certainty. And of course, there are many other uncertainties that we should include in our volumetric estimates, but they can all be addressed in similar ways to this, using different data types. So a little trip into the world of wells. This is also a very popular topic. Lots of people are publishing on this. But it's kind of the same setup, different data, so supervised learning. Take your well logs as the input in the feature set. These are measured continuously, basically all along the borehole, and pair them up with some version of the truth. And this is kind of the ideal manifestation of the ground truth, pieces of the ground extracted from the borehole, the core. And the core has been analyzed in the lab for porosity, permeability, and other properties. So from that, build your label set. And in any situation where you can get these pairs, feature label pairs, you can apply a machine learning model to quantify the relationship between them, use that relationship to predict the target property everywhere else where you do not have the ground truth. So we can produce all these logs that we usually produced in the science of petrophysics. And now that we have, let's say we have produced all those logs and we quality check them, we're happy with them. So now we choose to use them as the ground truth into the next step. So we make sure we position these logs correctly inside 3D seismic surveys. And we do some scaling tricks and so on. And now we can do another supervised deep learning method where the feature set is the seismic data, so the near stack, mid stack, far stack, for those of you who are into this, or the pre-stack gathers can also be the feature set. And the label set are these logs that we predicted in the previous step. And as it turns out, even though this is a very, very sparse label set compared to the enormous scale of the feature set, we can learn to predict these properties. So you see these shapes here. Again, these are the sand injectites, but now they are interpreted by a model that just trained on the data in the wells. Previously, the model trained on the data from the human annotation. So those are two different ways to embed ground truth into the machine learning models. There's one, the first one that we saw is using expert interpretation as the ground truth, and the second one is using direct measurements of the property of interest, which is porosity in this case. And as we saw in the previous talk, we also in petroleum industry, we use these geocellular models, and we can sample our properties into those and do our volumetric estimates. And all of this we have been able to do also before in various disciplines, manual seismic interpretation, to get the structure of the subsurface. We did petrophysics to predict the properties in the wells. We did seismic inversion to get the properties in 3D. And with seismic inversion, we solve the inverse problem with the seismic, and the output is typically acoustic impedance and so-called VP/VS ratio. But in these two images, these properties are not the outputs of traditional inversion, physics-based inversion, but we just predicted them with deep neural networks because we have access to acoustic impedance logs from the boreholes and VP/VS logs from the boreholes. So we can predict the same output that inversion gives us. But we can move beyond that. So inversion kind of stops at those elastic properties in the seismic case. But with deep learning, we can just jump to the next step and go directly from the seismic data to the property that we are interested in, which can be porosity, lithology, fluid saturation, and other properties. So you don't have to do these intermediate steps. You don't have to have a PhD in geophysics to run the tools. So we feel that this technology is very much democratized because it allows you to do work in disciplines that otherwise would be kind of off limits because you're not trained in that particular discipline. And these predictions are 3D. So just to look at the porosity cube, we can identify areas with high porosity. And it just so happens that we predicted a lithology as well. And so we can start integrating these different properties that we now have access to. We see that there's a clear link between the well world, the borehole world, and the seismic world. So we started with this little data in the wells to the left and moved to this huge amount of data after we predicted as a function of seismic. As scientists who know how we used to do this before, we see that these trends in the data still make sense. The lithology change and the fluid change in these elastic spaces. And we can highlight where our productive reservoirs will be and identify them in 3D in the seismic volumes. So I was asking a question yesterday, like when we can automate all these kind of mundane tasks, and this is happening, what will we do next? So one thing we can do is just ask questions to your data, because you predicted these properties in all the wells, in all the cubes, so you can start doing queries. And there we humans have an advantage. So we are creative, we know how to ask good questions, useful questions, and we will get answers. Another thing that we can do is embark on the second tier of development of AI for geoscience, is to take each of these boxes that I already highlighted and tie them together so that you automate across disciplines. So data flows from one type of analysis, and the output from that is the input to the next, and then all the way down to the lower right here, where you have addressed the volumetric, uncertainty, and decision questions. So that's kind of where we're focusing now. And of course, all of this technology needs to be available in a world where it consumes the data from an open data platform, illustrated below there. And it needs to do what it does with uncertainty at every step, not just uncertainty as an afterthought after we finish the evaluation. So that brings me to the end. So my message here is that the exploration and production industry, and I'm sure other industries represented here, need open data platform where we can access all this data. We can prove now that these basic workflows can be automated with machine learning. The speed up is an order of magnitude. We can take our human knowledge and ground truth information and embed them into the machine learning process. And we can make our predictions probabilistic. So then what I'm focusing on in my daily life is to make this kind of technology available to the generalist, the AI, the cloud technology, the data platforms, so you can come to work and exploit this in your daily job. So with that, thank you very much.
Thank you so much, Eirik Larsen, for sharing your solutions. Do you have any questions? Yes, there.
Yeah, thank you for a very interesting presentation. I was just wondering, have you done any confidence assessments of your models, like the automated porosity model? Have you checked the confidence and see how well your model performs?
Yes. What we always do is, like everybody else does, cross-validation. We hold out totally blind parts of the data set, and we check how well the prediction performs on data that was never exposed during training. We have kind of more advanced blind testing schemes where we kind of build as many models as we have wells, and so you build a model that uses all the wells but one, predict in that one, and take this well in, build a new model, all the wells without another one, so everybody gets to be the blind, and then aggregate all of that. So I think that's how we're building confidence now, this kind of blind testing approaches.
So what is your number?
It varies a lot depending on what you want to predict. But to predict in a well properties such as shear sonic from a wireline log set that has P-wave sonic and other logs, so you typically in the R2 in the 90s. But if you want to predict permeability, the inherent relationship between permeability and the logs is not that strong, so you're lower. And of course, it also depends on each case, how good your training data is, and how rich and diverse it is.
Question answered? Okay. Any more questions for now?
Yeah, Eirik, in one of your slides you showed an earth bank, and there was a data container labeled cultural data.
Yeah.
Can you comment on that?
Yeah, it's a term we use for data such as shape files of how we show a geological element on, well, somebody's acreage could be cultural data, an installation, pipelines.
Thank you.
Yeah.
Okay. Thank you. Do we have another question? Okay. Well, thank you so much, Eirik Larsen.
Thank you.
And we'll be chatting later again.